Good morning, everyone. Thank you for joining Megger webinar. I'm Grace Dunn. I'm the marketing manager for APACtsg, and I'll be the moderator today. This is a live webinar. You automatically muted to prevent any background noises. During the webinar, if you have any questions, please type into the question box, which you can see on the left of your screen. We will answer your questions at the Q&A session. At the end of the webinar, please have us fill in the survey, which you can see on the right-hand side. We'll be sending the presentation materials to those completed the survey. You'll be able to download an attendance certificate after you have finished the webinar and completed the survey. And the recording of this webinar will be sent to you in 2 days' time after the webinar. So today, our topic is a case study sharing on Narrowband DFR and IDAX322, presented by Michael Evangelista, who is our Meggereastasia TSG manager. Next slide, please, Michael. Michael is our technical support group manager for Meggereastasia. He started with Megger in 2016 as an applications engineer. He has a broad experience in different electrical applications and is appointed as the product champion for transformer testing. He is a registered electrical engineer, a native member of IEE of the Philippines, and a member of IEEE. He is also a co-author of a technical paper entitled Optimization of Power Transformer Insulation Tryout Process Using Dielectric Frequency Response DFR, which was published in November 2022. Over his 19 years of experience in transformer testing, relaying, and SCADA, Michael has contributed a lot to the electrical industry. He enjoys sharing his knowledge and experience through technical presentations and is always invited as guest speaker for many industry events. So let's welcome Michael now. Michael, I'll pass the time to you now. Thank you for joining us today.
Thank you, Grace, for the introduction, and good morning, everyone, or good afternoon, wherever you are. Like Grace said, our topic for today is about the narrowband DFR and the full DFR using the IDAX322. Okay, so let's start. But before we go to the main topic, let's do some review. Why we are doing this AC insulation test. This is important for our high voltage electrical systems because, of course, we need to determine the future or the reliability of our asset, like the transformer. And it detects issues before the permanent damage done. So we are trying to be predictive here. Okay, and also it will prevent accelerated aging of our system, of our transformer, for example. Now, going to the topic, I would like to review first the 3 steps of AC insulation testing. When we say of line power factor or line frequency power factor, we are referring to a 10 kV instrument wherein we inject 10 kV, but we are doing that normally in a nominal frequency like 50 hertz or 60 hertz. And the good thing with this line frequency power factor is that we can have the higher excitation current, of course, because we are injecting a 10 kV here. Now, for the assessment, we normally base it on the limits by the standards, which is good, of course. We have some limits at 20 degrees Celsius, right? And these are the limits, as you can see in the, for example, in the IEEE C57 standards. For the new asset, the insulation power factor or the tangent delta value should be 0.5%, not more than 0.5%. And if you have an old transformer or a service age transformer, the limit is 1%. Well, this is good because we have some sets of limits in the standards. Now, it is better if we can do trending. It is also stated in the standard that trending is the best for line frequency power factor, meaning to say we are comparing the previous test results. We are comparing the previous test result to our current measurement. Like, as you can see in this diagram here, year number 1, for example, then it will give us a better picture of how our insulation is performing. So in this one here, as you can see, there is a substantial change or abrupt change from year 4 to year 5. Then it will make us worry, of course. Then why it became why it went down during the 6th year? Maybe they did some purification, maybe they did some correction on the insulation. So it is better if you do the trending. Now there is another tool which give us a better or a best for this line frequency equipment. Okay, there is a better tool that we can use to analyze the insulation status of our equipment. This is what we call the narrowband DFR. We call it narrowband because it only runs from 1 hertz to 500 hertz. And by doing the narrowband DFR for assessment, it is not necessary to do the trending. We are comparing, for example, if you are going to test the bushing here in my picture below as an example, if you are going to do the comparison, it is very clear that this bushing here is different from the others. So no necessary trending. It will give you a better picture of your insulation status. And when you do the narrowband DFR, because we are talking of 1 hertz here, for your information, 1 hertz has a greater sensitivity in moisture, especially for moisture. Okay. Now we have the best one here, or not really the best, but what I mean is definitive, can give you a definitive answer. This is the full DFR, because when you do the full DFR, you are running the voltage injection from 1000 hertz or 1 kilohertz down to 1 millihertz. And by having this picture here, having these traces here or frequency response here, you can have the information about moisture, geometry, oil conductivity. Okay, and this one is a smaller equipment. Unlike the 10 kV, of course, you need a bigger transformer. That's why it's so heavy. While this one here, which also can give you the insulation status, is a smaller one, and it is lightweight. Now we do have some available equipment that can run the full DFR at 2 kV. This is the IDAX322. Before we have the IDAX300, it can also run the 2 kV, but you need to connect the VAX or the voltage amplifier, which is up to 2 kV. So we normally analyze the result by comparing our test result from the model curve. So for example, if you have this result, current test result, now you can see the deviation here, and that would mean maybe you have some moisture. If you have some deviation here, then maybe that would mean you have a problem in geometry. Geometry means on the physical deformation. And you can also see the oil conductivity, if it's still good. And also on this higher frequency region, you can confirm if you really have the problem with the geometry and the moisture here. Okay, and that's the full DFR method. So with the full DFR method, it will give you a conclusive insulation condition assessment. Now let's look at, or let's illustrate the difference of the 3 steps. This is the steps 1, right? Steps 2 and step 3. Now, when you are looking at the line frequency, for example, your nominal frequency is 60 hertz. You are just looking at this area here. It's very small. While when you do the narrowband DFR, then you can have this information here. From 1 hertz or from 500 hertz down to 1 hertz. While when you do the full DFR range, you can have the 1 kilohertz down to 1 millihertz. Okay, and this is the frequency range. The frequency range difference of the 3 steps. Why narrowband DFR? Well, when you are still doing the line frequency, of course, we are not saying here that you don't have to do the line frequency power factor here. Okay, you can still use it, but we are just saying we have some better method, or we have additional tool for you, because when you do the line frequency, sometimes it is uncertainty. When the line frequency power factor results change, we don't know what happened. If we don't have the previous test result, we have nothing to compare. And it requires trending of past result for effective detection of issues, like I've showed you. And when you do the line frequency, it's less sensitive to a moisture with less than 2.5% value. And for field evaluation of result, for example, you're already at the site, it requires more expertise, more knowledge. Now, when you do the narrowband DFR, you just need to add 4 minutes of your time and you can have the result for the narrowband DFR. And like I've said, narrowband DFR, it's more sensitive to insulation changes, especially on the 1 Hertz region. Okay, no trending required because you are just comparing the traces. It provides early detection of insulation and changes of the problem for liquid and solid insulation, and allows for cost-effective plan action versus reactive emergency action, of course. So that is the advantage or additional tool for you, the narrowband DFR. Now let's talk about the field observation of this narrowband DFR. Credit to this guy. This is Dr. Diego Robalino, our guru in transformer testing. Yep. We have these limits from the standards, right? If you, as I've told you a while ago, we have this 0.5 and 1 for the line frequency power factor. This is according to the standard. And we need to correct, every time we do the power factor, we need to correct it to 20 degrees Celsius so we can compare it with the limits of the standard. Okay? So here, they did some test for a new transformer using the narrowband DFR. So they have this frequency sweep, frequency response from 500 down to 1 Hertz. And this is the signature of a new transformer. Very clean, linear, it's good. They tried to test transformer, an old transformer. This is the service aids transformer number 1. And they got this result here. From 100 Hertz down to 1 Hertz. It's very clear that when you compare the 1 Hertz, the two are different. This is the new, this is the old one. But what does it say? Okay? Looking at the line frequency alone, well, you have the 0.27%, which is good according to the standard because a limit is 0.5 and 1. Right? But when you look at the 1 Hertz here, you have 0.7%. So what does it mean? Well, they did also a full DFR to confirm or to double check. Okay, so they did the full DFR insulation analysis and they got this result. Moisture is 2%, which is still good because our software for DFR measurement has automatic assessment. It is color-coded. Okay, so it is categorized as dry. And for the oil conductivity, it's still good. So meaning to say, when you look at only the line power factor, it's 0.27%, but we don't know if it is good or not because we don't have the past test result, right? Now we did the 1 Hertz and we got, we look at the 1 Hertz region when we did the narrowband DFR and we got the 0.7% measured using the 10 kV injection. And it indicates a good insulation, and it was confirmed by the IDAX here, or the full DFR. It confirms the insulation is good, still dry insulation, and with low oil conductivity. So transformer number 1 overall is good. And when you compare the narrowband DFR response, it's still good for the transformer number 1. Now this is the transformer number 2. still identical transformer with the transformer number 1. So they are the same specification, same year of manufacture. But what happened with this transformer number 2? When they did the narrowband DFR, oh, look at the 1 Hertz region here, the 1 Hertz value here compared to the new transformer. So it's very, noticeable, the difference, very noticeable. And when you look at the value carefully, with the line frequency or the 60 Hertz region, well, to me, this is fast because according to the standard 0.5 and 1, so this is still good. However, when you look at the 1 Hertz power factor value here, it's around 4% or more than 4%. So what does it mean? They did a full DFR on this transformer number 2, and it was confirmed that it has 3.4% moisture, and the conductivity is really a service age or an old one here. Okay, so this is very alarming when you see this kind of or this value for moisture is 3.4%. Now, conclusion: if you are only looking at the line frequency power factor, you might say, oh, it's still good, it's 0.5, but it is misleading, right? Because it was confirmed by the full DFR. And with the additional tool of 1 Hertz, for example, if you don't have DFR equipment and you have the narrowband DFR, this is already a good tool for you to analyze that our insulation or that insulation is really deteriorating. So here, again, it was measured with IDAX or full DFR method and confirms insulation is in poor condition, wet, and high oil conductivity. So when you compare with these three, this is the response of the new transformer, good insulation, but deteriorated insulation. It's very clear, additional tool for you. So this narrowband DFR is not yet included in the standard. There's no standard for narrowband DFR, but for Megger, we have some proposed limit here. This is the limit from the standard, remember? For 1 Hertz, we are proposing 1% for the new asset, and for a service age transformer, the limit is 2%. So this is just for you as additional tool. Okay, we are proposing that one. Now let's talk about the bushings. So what about the bushing here? Okay, so let's talk about the bushing. For the bushing, the limit is 0.4 for the new bushing, and if it is an old bushing, it's 0.5%. Okay, 0.4 and 0.5 according to the standard. But these values are corrected to 20 degrees Celsius. Okay, so for narrowband DFR bushing assessment guideline, we can evaluate by using the narrowband DFR. We can evaluate it with 1 Hertz power factor, and values should be similar, of course. We need to compare the values of the 1 Hertz region of the bushings, high voltage and low voltage side. It should be, of course, typically they are the same manufacturer, same year of manufacture, and same environment, same application, etc. Now, this one is an acceptable insulation for bushing, an example of acceptable insulation. Okay, so this is the phase A, phase B, and phase C. So when you compare the traces of the three, they are good. Okay, because not much difference here. Okay, now this is an example of a poor insulation. When they did this, I think in one of the countries in Asia, they have compared the traces of the 4 bushings here. And as you can see here, if you are just looking at the nominal frequency or the line frequency range, the dissipation factor is 0.3 for oil impregnated paper. For this bushing is 0.28, for this bushing is 0.31, for this bushing is 0.3. So it looks like this bushing is better. This bushing here is better than this one here. 0.31, this one is 0.32. But when they did the narrowband DFR or the 1 hertz, okay, this reveals the problem. This bushing is actually good at 0.28, 0.25, but this one here gives 1.58 at 1 hertz value. And this one here gives 0.27. So the assessment, this bushing is in bad condition. Why? So they did some further investigation. They opened the bushing, and what they see is that they found some X-wax, as you can see in the picture. Well, there is a new standard, the C5722-200 series of 2022. You can also see this picture there if you have read the standard. Okay. So they found some X-wax, and of course, they need to correct this one. Absolutely, this is a problem. They need to correct this. So for bushing, the proposed limit is 0.2 to 0.5 for the new bushing at 1 hertz value. Okay. 0.5 to 0.75 for a good one. 0.75 to 1.25 for the age, and if it is more than 1.25%, you need to investigate, like the case study that I've shown you. Okay, so this is my personal experience or our customer experience here in the Philippines. So in this example here, we have used TRAX for a narrowband DFR. And when we talk about TRAX, you have the access of to generator of 0.1 to 12 kV. So the maximum output current is 400. I believe it's 500 now, 500 milliamp. And you have the 1 to 505. So this is a narrowband DFR here. Better if you have the 1 hertz value. Of course, for the measurement, it uses red and blue and ground connection. It also uses the UST and GST setups. Test for functionality, you can measure the tan delta. You can also measure with internal 12 kV or external generator plus 25 standard capacitor. External step-up transformer control if you want. You can also do excitation current and hot color testing if you want. And the good thing with the TRAX is that it has the ITC or individual temperature correction. Maybe some other time we will have some webinar about the ITC. What is this? Remember that when you are trying to do trending, for example, right? When you do the trending, you always need to correct it to 20 degrees Celsius to have a reference temperature. Of course, you cannot compare your value at 30 degrees to a 40-degree value. So you always need to have a common point, a common reference, which is a 20 degrees Celsius. And besides, the standard says about the limits, those limits are based on 20 degrees value. So that's why you need to correct every time you do the power factor, insulation power factor test or the tangent delta, you always need to correct at 20 degrees Celsius. Now, in our case in Megger, aside from the table, from the standard, we can use the ITC. The TRAX has also the voltage dependency detection, meaning to say we are trying to look at our insulation and see the voltage dependency. Okay? Maybe on the next webinar we can discuss more about this, but these are additional features when you get or when you buy the TRAX. So in this example here, the customer uses narrowband DFR, uses TRAX with narrowband DFR. So they have tested the 2 identical transformers for station service. This transformer is more than 10 years old. No maintenance or oil purification was done before. And so they did the narrowband DFR to analyze the insulation of the transformers. So these are the results. Transformer number 1, wow, almost everything is red, as you can see here. And when you look at the graph and looking only at the line frequency, you might say that the capacitance between high to ground is still good, right? But everything is bad. And looking at the 1 hertz value here, it will give us a better picture. Look at the value here for the HG and the CHL. This is the most important insulation between the high voltage and the low voltage insulation. High voltage and low voltage winding, the insulation in between, for 1 hertz, it's around 7.4. Well, if you are only basing it to 0.6, you might still say that, oh, this transformer is still good. My limit is 0.5 for new and 1 for the service age. So, but looking at this value here of 1 hertz, oh, it is very revealing. You can say that this transformer has a deteriorating insulation. Okay. So comparing it to transformer number 2, everything is good here, especially the CHG. Everything is good. And look at the 1 hertz value here. But still, looking at the 1 hertz here, they have a more than 2%. So this is 3.8. So meaning to say, I'm just showing here how we can help you using the narrowband DFR assess your insulation. It is an additional tool. It will give us confirmation from the line frequency that this is really the status of my insulation. Additional tool. Okay? So this one here, because they are old transformer, of course, they need to be purified. We need to do some corrective actions. Okay? Because it has been revealed by 1 hertz that you still need to do it. So comparing the two, these are the result here. So I think, or I believe, transformer number 1 needs more attention than transformer number 2. Okay? So that is the narrowband DFR using the TRAX. Now let's talk about our new insulation tester, which is the IDAX322, and using the full DFR method. So we have tested a 100 MVA auto transformer. As you can see, it is 100 MVA here, 230 kV on the high voltage side, 69 on the low voltage side, and the tertiary is 13.8 kV. So before going to test, we need to take note of the voltages, of course, because we need to decide our test voltage. And we should not exceed the limit. I mean, we should not exceed the nameplate voltage rating of the transformer for our test voltage. Okay, of course, we need to take note the temperature here because we need to correct. Remember, if we are going to do the trending, if you are going to base your results to the standard limits, we need to correct it to 20 degrees Celsius. That's why we need to take note of these temperatures here. So because that is auto transformer and it has 3 windings, of course, I just forgot to put the picture of the 3rd winding here, but this is the winding 1, winding 2, and winding 3. They also have the oil temperature sensor here or meter. Of course, for the connection, you need to short everything, the bushing, connect it separate with the tertiary. Because this is auto transformer, of course, the bushings of the primary and the secondary should be shorted, everything. And then you can separately shorted also the third winding, the tertiary. And this is also important when you're going to test the bushing, then you need to look at the nameplate as well. And good thing with this bushing here has the values for C1. It's 413 picofarad and 423 picofarad. Maybe this is the maximum and this is the minimum value. For C1, we need to verify the capacitance value, of course. So when we do the insulation power factor of bushing, that is the first thing that we need to do. We need to check the value of capacitance first, because the value of capacitance will tell us if we are connected correctly. Okay, because if we don't have the same value of capacitance, so most probably your connection is wrong. So that is the first thing when you do the IPF or the insulation power factor. You need to check first the capacitance. Good thing with this bushing again is that we have these values here. We have the C2 also, 21,570 picofarad. And look at this, we have shorted the tertiary winding, and we have shorted the bushing of the primary and the secondary winding. Remember, this is an auto transformer. Now, to watch the actual testing we did, this is soon to be posted in our meggereastasia YouTube channel. Okay, so stay tuned. Let's watch the video on how we did the test here. So as you can see, this is a substation, a 230 kV system. So we are actually expecting some interference here because of course this substation is online. So we are expecting some interference here. This is a big transformer. Of course, we need to take note the temperature here. We need to connect the ground, of course, a common point. Look at this, how easy we assemble our clamps. This is the IDAX322. And you also have two interlocks, the key and the switch. You can connect it to your laptop by USB. Of course, we need to secure the shorting. We have shorted the tertiary, the nameplate. And this is the software setting. Maybe I can give some comments on the software setting here. So here you can select whether you want to see a percent dissipation factor or power factor. You can select the standard, whether you are going to use IEC or ANSI. You can also enable the oscilloscope so that you can see the current sine wave and the voltage sine wave. You can also select the generator. You can select 2 kV or 200 volts. You can also select the test leads here, and you can edit the frequency ranges here. Okay, when you enable the multi-frequency, your test will become faster because it is doing 5 simultaneous frequency. So for example, if you do a multi-frequency on the lower frequency region, it does 5 frequency at a time. So meaning at the same time, 5 frequency measurement. And you can also enable the polarization and depolarization current, or the PDC, if you want to. And here, you can also enable the conductivity in Siemens per meter or picosiemens per meter. And then, of course, you can also edit the material, if it is 2 materials or single material, or if it is oil and paper. Okay, so this is the setting here. Now it shows the oscillograph. You can zoom in the oscilloscope, I mean. And as you can see, it is 2 kV. Of course, we have a quick assessment. So it will tell you how much moisture you have, and it is color coded. So this color means it is as good as new. Okay. It also have the hookup diagram. And if you want the data, the number, not just the graph, you have this different frequency, different value of tan delta. You can also do the analysis if you want to change the barrier percentage, the stick percentage, or the material. And then you can export the report to PDF or to MS Word if you want to. And this is how it looks like. Yeah, that is the video and soon to be posted in the YouTube channel. Okay. Now, looking closely at the results of that testing here. So when we try to analyze the insulation between high and tertiary, because this is auto transformer, it's very clear that it has a good insulation condition. The moisture is only 0.2 and the oil conductivity is 0.208 picosiemens per meter. Okay. Now, uh, this is the analysis when you do the moisture assessment or moisture analysis. When you do the moisture analysis, remember this is a full DFR. We are comparing to the model curve our test result. So here you have the model and you have the measured. So it's almost in phase, in line. So yeah, it's very clear. No moisture. I mean, there is a moisture, but it's acceptable value. And when you do the ITC correction, you need to correct because this value here is at 33 degrees Celsius. Now, if you want to see the 20-degree value and if you do the trending in the future, then you can change the analysis to ITC. Now, the correction that we are doing here for the temperature is we use the ITC. We are not using the table here. We are using the individual temperature correction factor. And as you can see here, the power factor that we got is 0.257 at 20 degrees Celsius. Okay? So, yeah, of course, we need to compare, or I mean, to believe, okay, to believe that we are getting the same value as 10 kV, we compared the test results we got from the full DFR to the 10 kV test result. This is the line frequency 10 kV previous test result. So when we tried to compare the CH, the high voltage to tertiary here, the value of power factor is if I'm not mistaken, it's 0.256% power factor. That is the corrected one. And when you look at our result, it's 0.257. This is DFR. This is line frequency 10 kV. So it is very, very comparable, right? But this one, we tried to do, or we sweep the frequency, okay? Now, of course, test voltage matters when you do DFR, okay? Now, looking at the bushing here, we compared the 140 volts versus the 1,400 volts RMS, okay? So, in the 60 hertz region, or in the 60 hertz value, and using 1,400 volts RMS, you can see a slight difference, slightly different from the 140 volts. But of course, 1,400 volts is better, as you can see here. It displays 0.384. On the 140 volts, it's 0.386. So Yeah, a small difference, but very noticeable. And when you look at the 1 hertz, 1 hertz value here, also slightly different. For 1400 volts, you get 0.308 versus 3.10 on 140 volts. Well, we are just talking of 60 hertz and 1 hertz here. What if our stop frequency is around 2 millihertz? What will happen? Then that will make a big difference. At 2 millihertz 1400, our measured power factor here is 11.68%. This is already percent. And look at the 140 volts here. At 2 millihertz region, it's 14.19%. So it's around 3% difference, guys. And 3% difference is a big value when it comes to tan delta measurement or insulation power factor measurement. So meaning to say, test voltage matters here. Okay? Remember that we are doing this test in an online 230 kV substation, and we have a lot of interference nearby. And also, according to the IEEE standards, this is the new standard C57.12.200, that's 2022. This is a very new standard. This is a guide for the electric frequency response and measurement, response measurement of bushing. So look at this value here. It is very clear that the 1400 volts RMS is not affected by the interference versus the 140 volts. Look at the 140 volts here. This is the capacitance, sorry. This is the power factor here. Look at the 140 volts here. It has been affected by the noise. Okay, it's very clear. So also here, when you compare the 140 and 1400 volts test voltage, the 140 has been affected. Same as this one here. And you can find the same image in this standard. If you have the copy of the standard, try to look at it. You will see the same picture here. And it shows that the 140 volts RMS trace was clearly affected by the substation interference at frequencies of below 0.1 hertz, while the 1400 volt RMS trace was smooth, which indicates being less affected by the interference. Okay? So, conclusion, having 1 hertz power factor, this is a very simple and trending is not necessary. This is additional tool for you guys. Of course, we have some proposed limit as you have seen in the slides. And it was confirmed by the DFR. So you can use that for overall transformer, and also you can use that for bushing. Okay, so line frequency is good. Having line frequency power factor tested is good. However, of course, the reliability is limited, and you also need for better insulation trending, you need to have the previous test result. And this is our products for the line frequency power factor. But it's not always practical, of course, because what if you don't have the previous test result? Okay. Now, better if you can do the narrowband DFR. It increased your confidence in your asset assessment, and trending is not necessary. Additional tool for insulation assessment for you. But of course, it is the best if you have additional equipment, which is full DFR, because that will give you a definitive result. Gives it is a reliable indicator of developing problem, and it is smaller and lightweight, of course. And these are the products that we have. For the line frequency, we have Delta 4000 and the TRAX, which has ITC. Both have ITC and BDD. And for the full DFR, we have the IDAX322 that can go up to 2 kV in one unit. But we also have the IDAX300, IDAX350, wherein you still need to buy the VAX, the amplifier, for you to have the 2 kV. So these are the references, and yeah, you can also scan this QR code here to learn more about 1 Hertz. And thank you so much for listening. I hope I have given you some information about the insulation assessment using the AC testing methods. Okay, Grace, if we have some questions there, I'm ready to answer.
All right. Okay. Thank you, Michael. Thank you for a wonderful presentation. So now it comes to our Q&A session. If you have any questions, you can type into the chat box, and we will answer them one by one. And for those of you who are leaving, please remember to help us fill in the survey for webinar improvement. And also don't forget to download the attendance certificate, which is at the bottom control panel, an icon on the right-hand side. Just a little reminder, we will be having another webinar on the 21st of September. The topic is Introduction to Static Motor Testing. The time is 10 o'clock in the morning, Hong Kong time. So if you're available, please go to our website, www.webinars, to sign up for the webinars. So now we have the first question here. Michael.
Yes, right.
Yes, okay. The first question is, why the result of DFR is comparable or has the same tangent delta result to 10 kV injection at nominal frequency?
Okay, yeah, that is a good question. Yeah, because the first difference is that you have a smaller equipment here, and this one is bigger, right? That is the first difference. But why is it comparable? Because normally, if we do, yeah, I'll just make this one as a space. If you do insulation power factor or insulation assessment or insulation testing, we normally treat the capacitance, I mean the insulation as capacitance. So meaning to say we are getting the IC, the capacitive current here for insulation, okay? And capacitive current is equal to voltage multiplied or over XC. Remember, from college, we have this formula. And of course, XC is equal to 1 over 2 pi FC. So meaning to say you have voltage divided by 1 over 2 pi FC. So in short, it is voltage times 2 pi FC. All right. Now, when you do 10 kV testing to get the capacitive current, we are trying to vary the voltage here to 10 kV to get the IC. So this 10 kV refers to this thing here. While if you do vary the frequency, for example, if you just limit your voltage to 200 volts, and then just vary the frequency, it is the same. You are getting capacitive current, but this time by varying the frequency. That's why you have the same test results. This one varies the voltage, that's why it is bigger. This one only varies the frequency, that's why it is smaller. But still the same purpose, you are getting the capacitive current, and you can have that value of the power factor. Okay? Any other question, Grace? I'll just make this one as
the second question is, can I also use the narrowband DFR to other test objects like CTs, circuit breakers, and others?
Yes, of course. So remember, we don't need to have a previous test result. So if you are going to do a CT testing, for example, you have CTs. I'm just doing a donut type. Of course, it's better if you do the test to test a bar type CT. So here, I will just get the, for example, this phase A, phase B CT, okay? And phase C CT. So I will just use the narrowband to get the frequency response of these three, and then I will just compare it. For example, this is the response of A, this is the response of B, this is the response of C. So it's very clear that, you know, the phase A has a problem. So it's not really just for transformer and boosting. You can also use that for circuit breaker. You can also use that for instrument transformer and other insulation available as long as it is insulation. But of course, take note of the charging current of the capacitance. Of course, if the insulation has a higher capacitance, of course, you need to have a powerful test equipment. Okay, Grace?
All right. And the third question is, what is the difference of AC versus DC insertion tests?
Oh, okay. That is a good one because, of course, previously, or maybe some of you will say, oh, I already have insulation tester, DC insulation tester. This is already good, right? Maybe some of you will say that. But yeah, we have two methods for insulation testing. We have the DC method, which is our insulation resistance. Of course, Megger is well known on this one. We have the Megger insulation testing. I'm just saying, I am not saying which one is good here or which one is better, but I will just show you the difference. When you do the DC measurement, it is a time domain. Why it is a time domain? Because we are waiting. Normally, when you do insulation resistance testing, you need to run for around 60 seconds, right? You need to run for 60 seconds. That is the minimum, and that is the according to the standard. Why you need to have a 60 second? Because in the first few seconds, you have three different currents. Three different currents. Okay? You have three different currents. In the first few seconds, because you are doing a DC measurement, your electrons or your negative charge will move towards the positive. And that is what we call the capacitive charging current. Is that the current what we are looking for? No, it's not. We are looking on the leakage current. So that is the first current. It happens on the first few seconds. On the next, or at the same time, it is also doing the polarization. That is the alignment of the dipole. Okay? And the last current that we are seeing there is the leakage current, which is our concern. That is our concern. How much current is leaking in my insulation? So why 60 seconds? Because we are allowing these two currents to happen first. But we should not include this in our computation of resistance. Okay? We let them happen first. That's why we need 60 seconds, because we are sure after 60 seconds, the only remaining current that we are looking is only the leakage current. But of course, there are some test objects that it's hard to polarize. It takes a longer time to polarize. Okay? So that's why we have this polarization index and the electric absorption ratio. Okay, that is a time. You can see the my previous webinar about this. Okay, I think how to interpret PI and DAR in the previous webinar I did maybe 2 years ago. So you can watch that to see the full YDC or how to interpret PI and DAR. Now, while in AC, because that is already oscillating, okay, we are looking at the capacitive charging current versus the resistive current here. So we are looking at the total current losses, the angle in between, which is the theta, and the angle in this one is the tangent delta. So normally we are looking at the tangent delta. It's difficult to draw using the mouse, which is normally equivalent to cosine or approximately equivalent to cosine theta. Of course, they have some limitation. Okay, they have some limitation, only up to 20%. Okay. Other question, Grace?
Yes, there's one last question. Can also do DC testing or PDC with IDAX322?
Yes, of course. I am prepared on that questions. I am prepared because, of course, some of the competitor might say, we can do the DC, we can do the PDC. Of course, in our product here, the IDAX322, we can also do that. I'll show you. So this is the software or additional features of our IDAX322. So here you can select test modes or test application. So you can do DFR measurement, you can do DFR with ITC correction, you can just do pure DFR, you can just do power factor or excitation current because you are already doing a 2 kV. So you can now do the excitation. And you have the PDC moisture, PDC ITC1, and the PDC. So if you select PDC here, it will bring you to this display here, wherein it will give you the PDC value. So here, you can already have, using just the IDAX322. Remember your question about DC and AC difference? Well, if you want to do DC, that is also possible with IDAX322. You have insulation resistance, you have DAR and the polarization index value here using a 2 kV. And that is already a great feature which is added to IDAX322. Of course, there are some of you might say, can we do the combination of PDC and FDS method? Yes, of course, sir. We have here the PDC screen. It's some kind of combination, right? And we have here the FDS method or frequency domain spectroscopy method. This IDAX322 is a new one, and we have a new software, and we can do PDC and FDS as well. Okay, and thank you very much for attending this webinar. I hope I have given you some information, and I hope you understand my presentation. Okay, Grace.
All right.
Thank you very much,
yes,
everyone.
Thank you, Michael. Yes, thank you, Michael. I guess we don't have further questions. If you have any more questions, please send us email to megger@megger.com. We will answer questions by email. Just a reminder, you can go to our website, www.megger.com/webinars for our upcoming webinars. And thank you again for attending. The recording of this webinar will be available in 2 days' time. And don't forget to download the attendance certificates before you close the webinar window. Thank you, everyone. Thank you, our presenter, Michael, and also our panelists, Sumiti and Bernardo. We hope to see you again next week. Thank you. Bye-bye.
Thanks, everyone.
Thanks, everyone.